great pleasure this evening to welcome Dr. Robert Pinkel. Dr. Pinkel is Professor of Oceanography at SIO, and he's also Associate Director of the Marine Physical Laboratory here at SIO. He obtained his BA at the University of Michigan and his Master's and his PhD at UCSD, in fact here at Scripps Institution of Oceanography. In fact, he's been here since 1968, and in his very own words, he's unemployable elsewhere. Of course, that's totally untrue. We're very lucky to have such a distinguished physical oceanographer here. And his awards include the Walter Monk Award, and that's given in recognition of distinguished research in oceanography related to sound and the sea. He studies Arctic oceanography, but also tropical oceanography. So he has wide interests, oceanic internal waves and small-scale mixing in the ocean. And I'm sure tonight during his talk, he's going to mention the Doppler solar system. This solar system, acoustic system, he developed himself, and it's deployed on the SIO ship Ravel. But actually, it's much better known locally as the Pinkelizer. In an article last November in the San Diego Tribune, which was talking about warming in the Arctic, Rob is quoted as saying, "What's happening in the Arctic isn't subtle. It's happening very fast, and it's fairly convincing that on the scale of our lifetimes, very dramatic things will be happening." And so tonight, in his talk entitled Ice, Ocean and Eddies, An Arctic Perspective on Climate Change, I'm sure we'll hear a lot more. So, Rob.
Well, thank you. That is a hard introduction to follow. I hope I can be as polished. I'm very pleased to be here tonight. I'm also a little nervous because I'm going to be speaking of some things I know a great deal about and other things that I don't. In particular, I'm kind of a foot soldier in this battle of understanding how the climate works, not a general. And what I'd like to do tonight is to first introduce the larger problem as I see it, which is the area where I'm not really an expert, and then to show you how you go from such a big picture down to the things that I actually do in the lab here with my technical group and out in the field. And you can kind of see how the big picture relates to one specific job. So that's the name of the game. Now, typically when people talk about climate change, the first thing that everyone thinks is that someone's going to blame someone else for driving an SUV or something of that ilk. And I thought I would solve this sort of a blame problem just by going way back in deep time to times long before human industrial activity was a factor at all. And the goal is to just tell you a little bit about what the Earth is like even when nobody is messing around with the climate. And just to see a little bit what it's like all by itself. Now, the story, as I am comfortable telling it, starts in Greenland, which, as you can see, is particularly white. We're looking down on it here. And there are valleys in Greenland that are just like the Sierras. Some in the center where mountain ridges contain a valley or a basin that's more than a mile or so deep. And the difference between the Sierras and Greenland is that over time, these basins fill up with snow year after year and layer after layer. And at this point, there's around 100,000 years worth of snow packed into some of these valleys. And that accumulates, leaving annual rings, just like the rings on a tree. And people like Jeff Severinghaus here have been able to drill way down into this ice and produce very precise records of the temperature of northern Greenland for the past 100,000 years. This is, every science talk has to have wiggly lines, and I'll just show this, this one many times over. Don't be alarmed by the bell. I'm uncomfortable giving talks unless bells are going off in the background. At any rate, what we're looking at is temperature 20, 30, 40, 60 degrees, and you can see the scale's getting colder as you go down here. This is below 0, and it's a representative temperature in Fahrenheit of the Greenland ice cap. And it started off 100,000 years ago by getting colder, then warm, then cold, and over the middle part of this period, it's bouncing up and down incredibly fast. And what you see is about at this point, when things were at their coldest, that's when people crossed the land bridge over the Bering Strait and started to populate North America and South America. Then there was this little spurt of warmth about 14,000 years ago, cold again for 1,000 years. And then it rocketed up to this really warm state where it's been for the last about 12,000 years. This is, if you recall, when people talk about the dawn of civilization and the discovery of agriculture, this is when we kind of came out of the trees and started planting crops and so on. And you can see the fluctuations that our society has had to deal with are not much compared to the way the Earth has normally been bouncing around in the last 100,000 years. Now, the top of Greenland is a fairly miserable place, but the Russians have been able to discover an even more miserable place. This is their Vostok Station that's up at 10,000 feet in Antarctica, the other side of the world. And in that place, the ice goes down, it's packed even deeper, and they can drill back in time 500,000 years. So what the first picture was a little segment of a record like this from near the North Pole, and they're going back 5 times as far, and what you see is that it's kind of warm there 400 and some thousand years ago. Then it slides down to being cold, shoots up being warm, slides down, shoots up, slides down, shoots up, slides down, shoots up, and here we are today. And of course, for all the talk of global warming, if you look at that, and that, and how long we've been warm, you'd say, well, maybe we're in for a fall. Now, the scientists who read the temperature out of, they actually use the isotopes of oxygen, the ratio of oxygen 18 to 16 to determine the temperature. They're actually able to find microscopic bubbles frozen in this ice, which would contain micro samples of the ancient atmosphere. And guys who are a lot smarter at chemistry than I am have tracked the CO2 level in the ancient atmosphere back to that same 100,000 years. It's incredible stuff. And it looks, if you're worried about global warming and such things, you can see the CO2 in the atmosphere mirrors the temperature at the South Pole extremely well. And it isn't clear whether from this picture that the CO2 is causing the temperature to go up or down, or it's the other way around. But right now, let me just say, there is this awesome pattern of similarity between the CO2 in the atmosphere and the temperature of the planet. And this pattern's held for 500,000 years. I thought you might like to see how some of this data is collected. This is up at about 5,000 or 6,000 feet on the Greenland Ice Sheet, and this dome was set up, and this big tower erected, which is a little bit like an oil drilling rig. Inside the dome, you can see it's a plywood structure. All sorts of drilling equipment is set up, not to drill for oil, but to actually take out tubular sections of this ice and take it out in a way that doesn't distort it or contaminate it in any way. It's an interesting project to have scientists who can't let their samples melt or they'll lose everything. It's for oceanographers like me, I deal with digits and so bringing back hunks of ice is very complicated. The living conditions are really quite luxurious up there. Here's the dome with the drill rig, and these tents of various sorts are put up. And one of the interesting things about life on ice is that anytime you put any obstruction up, it builds its own snowdrift. And so anything you put down or leave, you have to prepare to be buried. And the last thing you take in when you go inside one of these at night is a shovel and an axe. So when you open the door, which opens inward, you can dig your way back out. Here's a close-up. Let me ask you to look at just the green line, which is a temperature record. And again, it's 20, 30, 70 degrees below zero, and it's a Greenland climate. This is probably work that Jeff Severinghaus had a role in. And again, this period about 14,000 years ago, when it looked like it was starting to get warm, then it cooled down and went rocketing up. And there are, of course, two levels of concern or surprise here. One is what's causing all this? And the second one, which is even more puzzling, is how does it happen so fast? When I first made this slide, the argument was whether this warming in this section took 10 years to happen or whether it happened in a single season. Now people are thinking it might be 3 to 30 years and have drops like this one go the same way. And again, all the climate variability we're used to are these little teeny wiggles up here. This warm wiggle is when the Vikings settled in Greenland. They actually called it Greenland, even though it was pretty miserable because they were trying to do a real estate development there. That's actually the truth. And here, this cooling period was enough to drive them out. And that happened around 11 or 12 or 1400. So this is the history we're used to: dust bowls, everything thrown in, El Niños. And this is what's going on. And a major issue is, how does it happen so fast? As you know, for those of us who live near the ocean, it doesn't even cool down very much at night because the ocean has an enormous ability to store heat, and it would take 3,000 or 5,000 years to cool the ocean down significantly. But it seems like the temperature in the atmosphere is changing incredibly quickly, and that's the way the planet wants to work. Well, in terms of all of these odd cycles we saw in the Russian sawtooth slide, there are astronomical reasons that can plausibly explain them. For example, the Earth doesn't go around the sun in a perfect circle, it's an ellipse. And the ellipse is not only rotating a bit around the sun, but its dimensions are changing. And the Earth doesn't sit and spin on its axis. The axis both tilts back and forth, and it wobbles like an unsteady gyroscope microscopically. And these things change the amount of solar radiation and its difference on the planet. But the puzzle is they change it by like 1% or less. So how can these microscopic changes lead to ice age or no ice age? Very interesting situation. This is Gary Larson's view of it. If you can't read it, it says, "The picture's pretty bleak, gentlemen. The world's climates are changing, the mammals are taking over, and we all have the brain about the size of a walnut." And that's the way scientists, of course, feel right now. In terms of being able to switch the temperature of the planet really quickly, without having to warm up the whole ocean, attention is now focusing on, of all things, the Gulf Stream. And this is where oceanography starts to sneak into the picture. Here's the Florida Keys, Chesapeake Bay, Long Island, our evil twin here at Cape Cod, and so on. And the colors here represent the temperature of the ocean surface. And what you can see from the point of view of a physical oceanographer, the Gulf Stream is really kind of a fire hose of warm water, and that water is heading up to the north and east, and it eventually goes all the way across the Atlantic and keeps Norway rather nice and warm. Norway is at the same latitude as Alaska or Labrador, and you'd think it would be freezing cold and with polar bears, roaming down Oslo streets, but it's quite warm, and it's because of the heat brought to the north and to the east by the Gulf Stream. Now, if anything were to turn that off, the temperature of Northern Europe could change like that. And here's a switch mechanism, as I simplified it down, of how you could change the temperature of the North Atlantic and hence Northern Europe very quickly. This red arrow down here is the Gulf Stream heading right now up toward Norway. Let's imagine that. And down here is America in the last picture in Canada. And right now, a small branch of the Gulf Stream heads up by Iceland and the islands of Spitsbergen. Here's Greenland, where we started out. And this water flows into the Arctic. And as it goes north, its temperature goes from incredibly warm to still incredibly warm, where incredibly warm by Arctic standards is 1 or 2 degrees above zero. So it's been cooling all along, and if you fell in it, you would not last long, but it's still, by Arctic standards, awesomely warm. And it's also very, very salty. It comes from low latitudes where there's a lot of evaporation. And it goes into the Arctic Ocean, and it spends a number of years circulating around the Arctic Ocean, and it gets even colder there, and it turns out even saltier. Now what happens right now is it comes back out after a 3 or 4 year stay, along with a lot of other water from the Pacific and from Arctic rivers. But that stuff is so cold and so salty that when it gets back to the Atlantic, it heads right to the bottom. And cold as it is, it goes down to about 2,000 or 3,000 meters and then spreads out on the west side of the Atlantic. And it's down there for the next 2,000 or 3,000 years. It's like sweeping all that cold temperature under the rug. Now, the bad news, and I'll give the Oceanography 101 slide in a second, is that the difference between having that water sink and having that water float are small differences of 0.1% in the density of the water. If you want to have water stay sinking, you know, if we like this warm temperature, we'd like to have this pattern continue to persist. And we'd like the water flowing out of the Arctic to be very dense relative to what it finds in the Atlantic. And it turns out to make heavy cold water, you have to keep it salty. So if you remember from chemistry class that pure water defines what a gram per cubic centimeter is, and the density of seawater is about 2% heavier than pure water, and the difference in density between the lightest ocean waters and the heaviest is also about 1%. The odd thing is when you get salt water, very cold, its density doesn't grow anymore. Most anything else, when you cool it, it gets heavier per unit volume. But for seawater, when it gets down near zero, the density isn't affected by further cooling. And if you want to make this cold seawater more dense so that when it gets to the Atlantic it's going to sink, you have to make it saltier. Adding salt will make it more dense. And the Arctic, it turns out, is the Saltshaker of the world's oceans. In particular, if you take salt water and you freeze it on the surface, what comes out is a variant of pure water, and the salt that was in the salt water drains out into the ocean below. So if we want to make the water flowing into the Arctic, flowing into the Atlantic, really heavy so it sinks, we want to have a lot of freezing going on in the Arctic Ocean. Now this is a bird's eye view of the Arctic. The oceans are blue everywhere but in the Arctic because here the ocean is usually covered with ice. It's a polar ice cap, and it contrasts with the South Pole where there's a huge continent down there. The ice in the Arctic is typically 1 to 2 to 3 meters thick, so multi-year ice is as thick as this room is tall. And if you want to freeze ice, it's nice if it's thin and it'll grow very quickly and freeze very fast. If you want to see a bird's eye view of what I was talking about, of warm water flowing into the Arctic and cold water flowing out, here's Greenland again, where we started the show. And here are the islands of Spitsbergen. And that branch of the Gulf Stream, instead of hitting Norway, is flowing up here, and it's warm enough to melt that channel in the ice. You can see that little channel? sailors who were whaling back then used to take refuge in there. They would count on that existing, and when storms were really blowing, they could get up in Whalers Bay, as it was actually put on charts, and get some protection. And that contrasts with after flowing around, the water comes out the east coast of Greenland there, and you can see this ice is carried by the really cold water all the way down the coast of Greenland, floating on top. And this water is much, much warmer, meaning several degrees centigrade, from this, or much, much colder rather, than the stuff just on the other side of the Fram Strait, where the water is going in from the Gulf Stream. So you see this very odd pattern of this long arm of fresh water going up, or warm water going up, and cold water coming down. And you can see that this Atlantic water here is going to want to melt the polar ice cap completely away, certainly interfere with the amount of freezing that's going on. But fortunately, as it gets way in here, it gets enough saltier that it sinks away from the surface and stops coming in direct contact with the ice. And this is where people like me come in, because I'm looking for processes that exist down deep in the Arctic Ocean, underneath the surface, that might take the heat from that water and mix it up to the surface and melt the ice anyway. And so we'll transition slowly from the big picture to a more focused one. Here's a picture of the Arctic Ocean in terms of its temperature in the Beaufort Sea, which is north of Alaska. And if you look at the very top part of the ocean, 100 meters, the height of SeaWorld Tower roughly, is about a degree below zero. And you can get below zero water without freezing, or because it's so salty. And you get down 300 or 100 meters, 300 feet, you go down to 300 meters, it's really warm and toasty, meaning a degree above zero, right? That's warm and toasty. And if this heat were to come in contact with the ice up here, it'd very quickly melt the polar ice cap. And guys like me are trying to make instruments which can look 300 meters down into the Arctic Ocean and look for signs of turbulent mixing, anything that could bring the heat from the down here up to the surface to melt the ice without actually bringing the water up. And that's the story. That's where I come into this story. Given the speeds that the Arctic Ocean actually moves, it's like standing at the top of Bright Angel Trail in the Grand Canyon looking down from the south rim and trying to measure how fast the ants are walking at that very first plateau that's down there. So it's not a trivial measurement task, and of course the weather's rarely as good as on the south rim of the Grand Canyon. Now, in 1997 and 98, the National Science Foundation ran a year-long expedition to the Arctic, and the goal was to monitor the health of the ice cover for a full 12-month year, check things out in all seasons. And oddly enough, the dangerous season in the Arctic is summertime, because you can slip, fall in, and it's you're 3 miles down. So to get the camp to last for a full year, they chartered a Canadian icebreaker and took it north in the fall of 1997 and froze it in north of Alaska. Just parked the thing and took off all the crew except for 16 people who were going to run the ship as kind of a skeleton operation over the next year. And this, I should mention, was a French-Canadian icebreaker, not to be contrasted with the British descendant Canadian icebreakers. And the proper style of Quebec, that's 16 Coast Guardsmen running this icebreaker. Of the 16, 4 were chefs. So it was a very, very atypical trip to the Arctic Ocean. I can't tell stories of, Scott running out of food and hitting scurvy. But what happens is the ship was quickly frozen in, and these pictures were taken in November when I got up there. An airstrip was bulldozed next to the ship so planes could fly in and out, and planes visited every 6 weeks. And power lines were strung. And a whole village was built up around the ship of these little tents, each with a heater in them. And some of these had holes in the floor so that you could access the ocean about, about 10 feet below. And some of them had gear for measuring the winds and humidity and snowfall. And the whole ship was instrumented with a host of meteorological radars and sensors as well. And so this was, the experiment was called Sheba. It was a surface heat budget of the Arctic. And this is downtown Sheba as it existed in November of 1997, power lines running and so on. You can see it's very, very strange for an oceanographer to be walking around the bow of a 300-foot vessel. But the French-Canadian crew immediately announced they were homesick and put the sign up. And otherwise, they were just incredibly fun hosts. The way you start work in the Arctic to do science is first by trying to get at the ocean. You're walking on 3 miles of it, but getting through that first 6 or 12 or 20 feet of ice is incredibly difficult. There's a lot of energy required. And the folks at the University of Washington made something that looks for the world like a steam calliope. You actually pour in kerosene and pump it up, and it smokes and it coughs and it sneezes, and it heats water up from frozen ice and circulates the hot water in a circle and slowly melts down and cuts out the cylindrical core in the ice. And when it breaks through into the ocean, you grab these poles and bring it back up, and then you have about 10 minutes to yank this core up, which weighs a number of tons, and slice it into pieces and get them out of there before the whole thing freezes solid again. This is kind of the landing stage of a D-Day operation. When you're out on the ice, you have just nothing to support you until you start getting through the ice to the water. These small tents can be dragged along on sledges with snowmobiles, and as soon as you have a hole with access to the water, you drag a tent over the top and get a heater going in that tent, and that'll keep your hole protected. And of course, this is Gary Larson's view of that. One of the downsides of this sort of operation is the Arctic is not friendly for people with glasses. And even though they joke about this, getting people, it's amazing how many of the ice blocks move when you don't have good vision up there. My own research involves measuring the currents, and we can't fly up a bunch of current measuring instruments and winches and stuff to lower them down. What we have are sonar systems that are designed from the ground up to measure ocean currents. And these are the exact analog of the Doppler radars you see on the evening news, except instead of electromagnetics, they use pulses of high frequency sound. And the pulses go out in these very narrow beams, and in this case down 300 meters, not 30. The sound scatters off the plankton that's drifting in the water. And these are ticklish instruments to build, so they're scattering from what a fish finder would see when there's no fish, or a depth sounder sees when there's no land underneath. That's the signal. And from these very weak echoes coming back, you measure the Doppler shift, or the frequency shift, and that tells you how fast the plankton were drifting with the water. And if the plankton are nice enough to not swim, that tells you how fast the water was going without actually having anything down there. So it's a very nice technology, very convenient, and has really changed oceanography in the Arctic. This is one such device. You're looking inside a tent, plywood floor, and this thing is the business end of a very high frequency sonar. It works at 600,000 cycles a second. Each one of these these brown discs is the equivalent of a loudspeaker that both sends and later can listen to the sound. And you make a sharp ping, and then you spend most of the time listening to the echo die away, and then another ping and listen. And this guy would ping 10 times a second. The steel pole was to get through the ice, and Eric Slater is a mechanical engineer behind this guy, and he's posing as a proud papa before it goes into the hole in the ice. Here's another view of a sonar going in on a tent that's just down the street from the first one. And we build these gantries inside the tent. You get to go from being a scientist to kind of playing Woody Woodchuck and building these structures and lower the gear down through the hole in the floor. And the electronics here are wide open and exposed because we're working on them still. But eventually they'll be sealed up so that as the climate changes inside the tent over the year, condensation and the like won't affect the operation of the instrument. This is the sort of record that you can see with one of these devices. And here we are looking from the sea surface down the height of SeaWorld Tower here, 200, 300 meters. So we're going down a tenth of the depth of the ocean almost. And we're looking at the month of December from just at Thanksgiving on November all the way through after Christmas in December 1997. The colors here, you can think of them as representing east-west velocity. It's in fact the shear, the sliding of the ocean, but you can think of the red as a velocity to the east and this funny greenish yellow velocity to the west. And what you can see in all of this is that the interior of the ocean has all these odd stripes running through it, and they're propagating along. So as time increases, as you go from like the 18th to the 21st of December, this ridge is getting closer and closer to the bottom of the ice, and then it kind of dies out, and another one comes up the next 12 hours later, actually. And these things are internal waves. They're wave motions that propagate in the Arctic. And it turns out that when you look under the ice, it's filled with these very regular patterns. And these are the things that I originally thought might be causing enough turbulence to mix the Atlantic water, which is right down here in the bottom part of the picture, to mix the heat from that up to the upper ice cover, which is right there. The other thing that's not so clear in this picture is this funny shape here that passed on December 8th. What this is an Arctic eddy. It's nearly a perfect classical flying saucer coming, spinning its way along in a clockwise sense under the ice. And the diameter is, the radius is 5 kilometers, the diameter is 10 kilometers, 6 miles. So you could imagine a layer of water the thickness of SeaWorld Tower stretching from here to La Jolla. And this thing is spinning around in slow motion, and it makes a revolution a day roughly, which for the ocean, spinning once a day is a very fast spin. And it turns out about a third of the interior of the Arctic is filled with these eddies spinning around, and barely anywhere else on the planet. So it's a very unusual feature of the Arctic Ocean. And these things cause potential for mixing both at their top and at their bottom. You can see my signal dies away into this fuzzy stuff right where you get into the Atlantic water. That's nature's way of saying that the zooplankton population, the bugs, have also gone away down there. So it's too bad that we're battling against nature there. Here's a close-up of an eddy. This is taken in the eastern part of the Arctic. And again, the colors are velocity. So a red color here, let's see what, it's the north velocity component. Red color is going toward the north, and the bluish colors are going toward the south. And the actual eddies drifted under the ice starting on the 23rd, at noon on the 23rd. You see this big blue streak happening. The currents all of a sudden go from these yellowy colors, which is not much at all happening, to southward velocity at 25 centimeters a second. And it's like the edge of a hurricane going by in extreme slow motion. And here by late on the day, the 24th, the eye of the hurricane, the core of the eddies going by. And here, a day or two later, the other side goes by, and the colors don't turn dark red, but they get much more reddish. You see these very odd stripes, which are in fact waves that are shaking the eddy and making it really look like a grade B movie flying saucer, which is kind of both shimmering as it rotates, as it passes under. And the turbulence that's generated at the top and the bottom of these eddies turns out to be much bigger than the turbulence that I thought I was going to see from the waves themselves. And we can now follow up on that by trying to do a census of these eddies in the Arctic, try to see what causes them, and see if they can make a significant difference in terms of the health of the ice pack. So that's the kind of the quick tour of my research thrust. And these things, again, the downward propagating crests are waves that exist in addition to the eddies under the ice. And the typical velocities associated with these things north of Alaska are plus and minus a centimeter a second. So indeed, a full-on velocity is like watching the ants crawl. Not every day in the Arctic is a fun day. When the wind blows, the ice can come together, and as pieces of ice come together, there's a battle to see who's going to win, and often it just crumbles up both edges of the ice. And this was a particular day when we woke up, had a nice breakfast prepared by our French team of chefs, and someone called out that the tent that had all of the valuable snowmobiles in it was about to go under. And here you can see it's lifted up about 7 feet in the air and tilted, and all of these blocks are kind of rumbling around in slow motion. And Dean Stewart, who is a braver guy than I, is revving these $5,000 snowmobiles up to full speed. He's taken a knife and cut the edge off the tent, and he's just shooting them full speed out of the tent to try to get them to safe ice. And I'm on the other end of this rope with a bunch of other people trying to get them to not crash down in the rubble. It's just really, some days in the Arctic just aren't so good. And here's a day that had particularly singled me out. This ice floe is a mile around, and this is our tent where that nice blue sonar was. And you can see that God was not on my side that day. And it looks like a freak act of nature, but actually, again, we built this nice tent, and the snow drifted up around it. And both the heater in the tent and this extra snow made for a warm spot on the top of the ice. And just the difference between that warm spot and the minus 30 degrees on either side is enough to encourage cracking. And so there's kind of a history of bad luck like this. And what's going on is 2 weeks of work to set this instrument up are being undone as quick as we can. Everything, the power is being shut down, and we're trying to get $250,000 worth of gear out of there as the ice is slowly moving apart. And
how wide apart in the foreground is it there?
It's this wide in the foreground. It's just telling us it's licking its chops, waiting to eat that sonar. The beautiful blue sonar that I showed in the slide now is covered with teeth marks from one of those giant Paul Bunyan lumber saws that was used to carve the thing out really quickly because we didn't have time to waste. And we actually were able to hook a snowmobile up to the tent and yank it off the spot too. So we didn't lose anything from this one except for 2 weeks of work. Well, that's kind of what a feel for the research. Most ice camps don't have a nice ship with 4 French chefs, and most of the time you have kind of a typical ship's cook, and you live completely in tents and fly in and out in airplanes. But as was mentioned in the introduction, I came here in 1968, which is not quite 40 years ago. If you look at this summary slide of what's happened in the time since I've been a Southern Californian, the colors represent the change in temperature per decade in degrees Celsius. So 2 degrees per decade of a bright red here means it's warming about 5 degrees Fahrenheit per decade. Blue is cooling. And you can see over much of the Canadian Arctic, Alaska, and the Western Arctic Ocean, and all of Asia that has been measured, it's warming up really quite fast. And this is an average up until about 10 years ago. It corresponds to 20 degrees Fahrenheit. since the time I started to read about Harold Sverdrup, our former director, who was up here in World War I. The black areas, spots that just aren't being measured over that period. You can see if we're really interested in having a cold Arctic, lots of freezing to make the water that flows into the Atlantic salty, this isn't a good trend. Here is the Russian Vostok data again, going back 500,000 years. Here's our temperature in Antarctica, going through the several ice age cycles and up to our current warm period. Here's the corresponding CO2 that comes from analyzing these micro bubbles in the ice. And here's where CO2 is going to be by the end of the century in our atmosphere. Now, what that will do, I don't know, but it's going to be exciting probably. At any rate, I don't want to, scientists are known for doom and gloom, and Gary Larson, of course, had it right in this regard. But there are a couple things for sure. This is his second view of it. The ice ages, the temperature changes remarkably rapidly. In this picture, he is showing, a block of ice, a glacier that happened incredibly rapidly. The glaciers take 1,000 years or more to build, but the temperature that causes them can change in the course of a single, presidential term. And so what I'm saying is that, let me just encourage you, while the news is always full of the crisis of this and the crisis of that, there are lots of things that go on just slow enough to escape their attention. And as in this cartoon, I encourage you to go beyond the evening news and look at that sort of stuff yourself and keep an eye on what's going on the planet that happens fast enough for us, but a little slower than would make for television. Thank you. Question is, what about other techniques for making measurements that might back up this story that's coming out of the ice? And the thing that's really interesting is that almost every corner of the earth sciences, except for mine, is playing a role in this discussion right now. The folks here at Scripps who core the sediments in the deep sea find that with each change in temperature, different plankton populations appear, and the plankton populations change within maybe 5 or 10 years of the temperature changes because they live right at the top of the ocean. And so the sedimentologists are really into the game. And people who study old corals, the corals grow in rings just like trees. And if you can find a hunk of old coral that was destroyed in a storm, maybe the storm happened 50,000 years ago, you get a little hunk of 1,000 years of what the temperature was like during that period. And I could probably think of a lot more of these techniques. I'm unfortunately an expert in none of them. The interesting thing is that sometimes the records across the globe go up and down very quickly. In some of these cycles, one will go up while the other goes down. And so hunting all of the clues that one can get from all the different parts of the planet really helps to fill in the picture of what might be the actual patterns that occurred. And people are using every technique that they can get. Half and half. So at some periods they correlate, and some they don't. The big 100,000 year warm and then cold, warm and then cold, those things correlate. Yeah, I'll say this. I went as far as buying it, but didn't read the article yet. So that's one comment. I have a little difficulty believing that that the real differences in this most recent cycle, why this warm period is so much longer than any preceding one. Here's the way they show it. You can see that some of these warm periods were very, very short, and this one seems to be hanging on now. 10,000 years is extremely long. So there is an article in Scientific American that says that agriculture, starting from day one, was enough to change the climate, and I haven't read it, but it's going to be hard to convince me, I think, because at this time agriculture was, you know, a carrot patch somewhere between the Tigris and Euphrates rivers. So that I'd be willing to learn, but I haven't read it yet. Yeah, well, there are, you know, in spite of the historic tendency for scientists to not have anything useful to say, there's been an enormous effort to think of this, because we're all participating in some experiment, and scientists are the ones that have the most experience with experiments going bad. And the shining hope of 10 years ago was that if one added a little bit more iron to the ocean, the plankton would bloom more vigorously, and plants are consumers of CO2, of course. And it's more recently appreciated that when the plankton die, or the plankton are eaten by animals, which respire and give off CO2, and keeping track of the total carbon, you're not going to win nearly as much as one hoped. The numbers are still out on that, but in terms of other great ideas for how to mitigate this problem, I don't know of any that people are excited about. One is, I guess, liquefying the carbon dioxide and pumping it way down into the bottom of the ocean, where it will perhaps stay frozen under very high pressure. And that, I don't know how much energy it takes to do that, but if it's coal-fired, I don't think it's going to win. The people are looking at that closely as again sweeping the carbon under the rug, but it's an uphill thing. If we completely stopped all our CO2 emissions, just the present industrial revolution would take about 300 years to blow through the system. Well, these eddies were surprisingly more effective at doing the mixing than my beloved internal waves were. So that is one comparison. And they act over a long period of time to transfer the heat from 300 meters down up into the mixed layer that's just below the ice. But the water from Arctic rivers is totally fresh. It flows into the Arctic Ocean, which is actually more like a drainage pond surrounded by big rivers. And the salinity just under the ice is very, very low. And it insulates, that very cold fresh water insulates the ice from the warmer stuff that's just a little bit down in the mixed layer. When a storm strikes, the ice starts to move fairly fast, where that's fairly fast is maybe a mile an hour or two, but that generates enough turbulence to mix up this layer of fresh water and bring really warm water into contact with the ice. So we had a storm in this camp in March, and it was the very coldest time of the year, but there were about 50 watts per square meter of heat coming up into the bottom of the ice, which in climatological terms is a pretty big number. Well, it's been waving back and forth, and people now are monitoring very closely just what is coming out of the Arctic and trying to get a correlation between the position of the Gulf Stream and what comes out. And the picture that I've showed was state of the art when I made the slide 2 or 3 years ago, but an enormous more has been learned of subtleties. So far, the Gulf Stream is not showing any signs of wanting to move down and warm North Africa instead of Norway, but it's thought that that's what it does do in an ice age state.
Well, thank you very much, Rob. I'm sure he'd be delighted to talk to folks if you wanted to come up afterwards, but thank you again.
Thank you.